Hello, I'm Lawson McVay, and this is my project, Form Finding of Deployable Mesh Parabolic Reflectors. I'm in the Aerospace Engineering and Mechanics Department with Dr. Sichen Yuan. A parabolic reflector is a type of curved surface that has a paraboloid cross-section. Their applications are numerous and include long-distance communications, deep space astronomy, and military applications. The concept is pretty simple. All incoming waves perpendicular to the axis of the parabola are reflected precisely at the focal point, where a central feed is placed to receive those signals. At sufficient distances from signal source, all incoming waves are approximately perpendicular to the parabolic axis. Conversely, the reflector can be used to transmit signals in a specific direction by first emitting them from the feed and then reflecting them. Currently, there are two major design avenues for parabolic deployable mesh reflectors. The first is the umbrella type reflector, which uses radial ribs to support mesh panels called gores to approximate the surface of the desired paraboloid. Accuracy of the mesh matching the intended parabolic surface and the ribs of the umbrella type design cause large periodic surface errors, and additionally, thermal effects are much more significant for the mesh than for the ribs, which can cause inadvertent slackening given the thermal extremes typical of an orbit. The second design is the tension truss. This design divides the surface into polygon facets, which are then displaced to the desired paraboloid surface with vertical forces called tension ties. The design is what we'll focus on here. An example of a tension truss design is Northrop Grumman's AstroMesh. The design features two symmetric paraboloid nets within a deployable truss circumference, attached with tension ties. A radio frequency reflecting gold-plated mesh is stretched against the convex curve of one of the nets. This design is more thermally stable than the umbrella type reflector and exhibits a higher degree of surface accuracy with less manufacturing difficulty. Form finding is essential to tensegrity-based designs like the tension truss reflector. Given the topology of a network consisting of nodes and cables connecting those nodes, how do you determine what shape it will form? Equilibrium, that is, when the nodes of the structure experience no net forces, can be found through a variety of methods. This is not a trivial task, as the equations relating the node locations and the cable forces are a coupled nonlinear system. I'll cover three existing methods for form finding, two statical and one kinematic. The first method, which is a statical method, is the force density method, first proposed by H.J. Scheck in 1973 to facilitate the design of the Munich Olympic Stadium. While tensegrity structures had been developed for some time already, methods of modeling them and their measurements were limited and largely non-analytical. For example, they would make small models and try to extrapolate measurements of that, which is not necessarily best practice. The force density method proposes that the nonlinear equations could be reduced to a system of linear equations based on a force density parameter, which is defined as the tension in the cable divided by its length. Yes, that equation should be S over L. This method requires that the force densities be known or prescribed in advance, as well as some fixed nodes in the geometry to ensure a structure. The result of the derivation of this method is that the coordinates of the equilibrium state are dependent on, firstly, the network topology, which is described by the connectivity matrix C, the force densities, Q, which we defined earlier, the fixed nodes, and any out-of-plane stresses, such as those tension ties. The in-depth derivation isn't necessary to cover, but the main result is that this is a linear system of equations and thus can be solved analytically. We prescribe the force densities for our model to be uniform, meaning that every cable has the same force density. The connectivity matrix is inherent to the topology we chose, which is kind of arbitrary, and we chose the outer ring of the topology to be the fixed nodes, similar to the AstroMesh design. We use the force density method to find a two-dimensional net on the xy plane, which is then projected vertically along the z-axis to the paraboloid surface of choice. And you can see the result of that projection there. Although we constrain the force densities to be uniform in the force density method, the resulting tensions are generally not uniform without fine-tuning the force densities, which is not ideal for an analytical solution. Uniform mesh tension is important for a variety of reasons. Firstly, the cables will follow the geodesic lines of the parabolic surface, meaning their paths will be the shortest possible ones, and the material required for construction is minimized. This also means that the weight of the structure, when sent into space, is also minimized. For this reason, we call that a geotensoid. Additionally, this is the most stable configuration, allowing the reflector to better withstand small perturbations, such as thermal effects, And finally, a geotensoid allows the mesh to conduct electricity predictably and therefore maximize reflective capability for like a radio frequency reflector. Mortaro proposed a new method based on the force density method that typically results in the geotensoid net. This is the second statical method that we're covering. Given some topology, we guess an initial set of coordinates and the force densities. We then apply the force density method, vertically projected onto the paraboloid, calculate the vertical tension tie forces, and calculate cable lengths and tensions. Then we test the model for uniform tension, zero net nodal forces, and minimal difference from the previous iteration's nodal coordinates. If any of these tests fail within a certain tolerance, we recalculate the force densities using the equation there. The mean tension is calculated over the entire surface. This iteration is completed until all three tests are passed. We guessed the initial coordinates from our first force density method. Since we're already using the force density method in the iteration, it just makes sense to start there. But theoretically, you could use random coordinates as well. Using the tolerances listed here, our model converges in about 38 iterations. It's important to note that this method does not converge for every net configuration, especially those with fewer fixed nodes on the outer perimeter. There must be some amount of fixed nodes in certain directions. Dynamic relaxation is the kinematic method, so this one is opposed to the statical methods of form finding. And it's first described by Alistair Scott Day and refined by Barnes. We begin by an initial random guess and then compute the internal forces from prescribed member tensions. We could choose uniform tensions, but theoretically any tension distribution could be implemented here. Then, approximating the nodes as point masses, we calculate their velocities and positions with Newtonian mechanics. We do a check for zero net nodal forces, equilibrium, and then repeat if failed. This is the result of the dynamic relaxation method. And you can see the convergence of the random nodes to the net. This configuration takes many more iterations than the force density method, but it's not particularly computationally intense, and the results are almost exactly the same. That's expected because there should only be one uniform tension configuration. Near-term future work includes working with off-center feed models in which the dish does not take up a symmetric part of the paraboloid. These are commonly used to reduce the amount of physical interference the feed causes when receiving or transmitting signals. And they're typically defined by taking some cylinder at some distance from the axis and cutting that surface of the paraboloid. Additionally, surface accuracy calculations using root mean square errors should be done to investigate the closeness to which the methods approximate the paraboloid of interest. Surface accuracy is extremely important for space antennas, and choosing the correct faceting method can help mitigate any undesired fluctuations. Any questions?
Yes. How do you select what force densities to use?
Great. So in the initial force density method, we use just uniform force densities for simplification. You can note that a negative force density is going to correspond to a bar, and a positive force density is going to correspond to a cable. So because we have a net of cables only, then we're just going to use positive force densities, and it's easy to just make them all uniform.
In what ways might combining corrosion measurements with mechanical testing help validate AFSD as a reliable repair method?
Not sure.